So this week we're going to go over some refrigerated case components, some more commonly seen components when doing refrigerated cases. You know, cases being could be a reach-in case, a bunker. You know, could have a door, might not have a door. But when we talk about cases, we're talking about the equipment inside the stores that hold the product, right? And so some of the more commonly seen components on these systems, of course, there's other systems made by Novar and other manufacturers but what we're focusing on right now or paying more attention to are Sporlan controls. And they use what they call an SC3 controller on the cases themselves. For walk-in coolers and freezers, we'll see something called a KE2 controller. Essentially, they do the same thing. They have the same inputs and outputs. There's just a different application, right? So we see terminal blocks, we see relays, liquid line solenoids, temperature sensors, EEPR or EEVs, which stands for electronic expansion pressure regulator or electronic expansion valves. We may see one of these types per lineup, or we may see a combination of one EEPR and several EEVs per lineup. I think what is more common in our installation is going to be one EEPR per lineup and no EEVs, I think is our most common configuration. Then you'll have display modules. We see these on the front of most of our cases now. This where you can provide some controls of set points. You could provide some overrides for your lights, for your defrost, and things of that nature, which can assist in troubleshooting the cases. And I imagine that our techs do some direct input to these when starting these up, at least when they're not on a program yet or not connected to a network yet. That would be my assumption. And then we have CT sensors here, and a CT sensor in this documentation is called a current transducer. And to electricians like myself, we might call that a current transformer. Basically the same thing, where it takes a larger current or a larger electromagnetic field to create a smaller one, and then the smaller electromagnetic field is used to feed back into an S3C controller to indicate whether or not something is running, or if it's running at the appropriate load, or things of that nature. So here's our S3C case control. Basically, it's a compact computer specifically designed to control a refrigerated case. It takes inputs just like a desktop computer would take inputs from your keyboard or from your mouse, or from values generated by a program that you're running. Those things would all be inputs to a computer system, and then it has outputs to provide actions. So you may have something like a temperature sensor that is reading a certain resistance value, and based on that resistance value, the computer translates that into a temperature, and then based on what that temperature might be, it will signal whether or not fans should be running or defrost should be running, to what degree your EEPR valves should be open or closed, things of that nature. So yeah, it's just a computer with inputs and outputs built for a specific purpose. So here we have a fully connected S3C controller. Now, it's not the case that every single input and output will be used in every instance. This is just showing everything connected if you were to have everything connected. So we have things like our various temperature sensors. We have one here for coil outlet, discharge air, return air, and defrost termination. So these are 3 different temperature inputs, but we may not use all of these in every instance. I don't know that we use defrost termination in every instance, because it may be that we have medium temp cases, and those are unlikely to have defrost unless it's like a dual temp case or something. We may be using discharge air instead of return air to provide inputs to indicate temperature of the coil, right? So we might not have everything in here. There may not be an occupancy sensor. Maybe there's no lighting. It could be an unlit case. And so why would you have an occupancy sensor, right? So this is just it's showing a fully connected system. What components we actually will have would be indicated really on, like, if we go back to one of our drawing sets that shows what we have connected to our system. And this is, I don't know if this is not very clear actually on the screen, but you can see there's only a couple terminals shown here. I think actually this is an incomplete. It's not showing every connection here because I believe we do have more connections, but we may not have every single terminal used. Really just dependent on what the system requires, right? So we usually have terminal blocks that we're terminating our wires to versus terminating our conductors directly to the controller. We're typically terminating to a terminal block. So I have a couple examples of a terminal block here. Doesn't mean that we couldn't terminate directly to the controller if the terminal block wasn't there. It's just not what we typically see. There's some good reasons for having a terminal block in the system or in the assembly. One would be perhaps that replacing parts, having to put a screwdriver on this terminal would just increase the likeliness that you might damage the sensitive component. And so by having a terminal block, it sort of isolates that to some degree. But anyways, this is sort of what we see. We see terminal blocks typically. And so there is, what I wanted to show with this illustration was there is a type of terminal block we see, and I think I saw it in some pictures I saw of one of our recent stores, where the termination is not a screw style termination, it's a pressure terminal. And so the wire is pressed into the opening. And then to release the wire from the terminal block, you need a micro screwdriver to push into this opening here. So you see where this green screwdriver is going into this opening, it pushes on a spring and will allow you to remove the wire. On this illustration, it's this orange component here. If you push your screwdriver into there, it pushes down. You can sort of see how the mechanism here is built, and it will open up the spring, release pressure from the wire, and allow it to be removed. Just in a picture of some micro screwdrivers, something that anyone who's doing building automation systems should have. I think every electrician should have a set of these. If you're doing your typical branch circuit wiring, power distribution, things of that nature, you may not use it that frequently, but it's just a good tool to have in your bag when you need it. Okay, so relays. This is a very common component that we see not just in refrigerated systems, but for motor controls, for lighting controls. Relays is a component that we should be very familiar with as electricians. Relays are devices that open or close when voltage is applied to a coil or a solenoid. In the instance of electric defrost, lighting, or anti-sweat control, the S3C controller would enable a 24-volt output to control a remote relay. And this is done for a few different reasons. One may be that the current rating of the S3C controller is only 6 amps. So this controller, these outputs are rated, most of them are rated at 6 amps from the literature. The electric defrost is typically going to be pulling more than 6 amps, right? Lighting nowadays with LEDs probably doesn't pull more than 6 amps, so you may not see a contactor on newer cases for lights, but I would imagine for older cases that are carrying a higher lighting load, you may see a contactor in there for lights. Your fans, you may or may not see a contactor in there for fans. I think they tend to draw 1.5 amps or less. The fans, I may be wrong on that. Someone can correct me if I am. But you may or may not see a contactor as frequently on fans as you do with electric defrost. But these terminals are only rated for 6 amps at 240 volts. And so whenever you're going to approach 6 amps or exceed it, you certainly are going to need a relay. Okay, so here are some different examples of different relays. This one on the left would be more of a general purpose contactor. You might see one like these two on the left more frequently for your electric defrost. These the contacts on these have a higher current rating, and we can kind of see that in this picture here, where it's given us our current ratings at various voltages. At 120 volts, this is rated at 5 horsepower. Actually, I'm not seeing where the contactor rating is, but this is probably it says 60 here. It's kind of, all right. So these are more general purpose contactors rated for a higher current. Now this one here, the third picture to the right, third and fourth picture, these would be more like control relays. So, you know, these would have normally open and normally closed contacts, and they would be responsible for handling situations like if-then situations. So the scenario might be if component X is on and component Y is on, then Z. So, you know, these are more meant to control a sequence of operation, these smaller type of contacts. So here's an illustration of what a relay looks like. What are the internal components of the relay? And so if anybody remembers from science class, where at least when I did it, we had the 9-volt batteries. They gave us a nail and some wire, and we took the wire, we wrapped it around the nail several times, and then we connected it to the battery on both ends. And then what does that do to the iron when you wrap a wire around iron? That would, and then we call that a coil, and then connect voltage to it. Can anybody tell me what happens to the iron?
It magnetizes it.
That's right. It magnetizes it. And it's not permanent. It's temporary. And so you can apply a voltage to your coil and magnetize the iron. And then when you remove the voltage, it demagnetizes. And so what's happening here is we're magnetizing a coil. You can see where it says this energizing coil. This is your coil supply voltage, and this would typically be your control voltage. And so we have the yoke, or one end of the iron exposed, that becomes magnetized. And then we have an armature here. When this gets magnetized, it pulls the armature towards the coil, which then in turn pivots this upper end of the armature, will pivot upwards in this illustration, and then push this rod, which is connected to your common or your incoming voltage, would push this rod up towards this other contact. And so that what will happen then is voltage would come in on your common, and if it's de-energized, it will go out on this normally closed. And if it's energized, this will pivot upwards, make contact with this upper rod, and allow current out to flow out on this normally open contact. So based on that explanation, in a de-energized state, what position are these contacts in? Can anybody tell me?
Right now, you're normally closed.
Right now, normally closed is in what position? Open or closed? If it's de-energized, what position is normally closed?
It would be closed.
Closed.
Yeah.
Yes. Yeah. This is how folks often get like a little nervous about answering. But that's exactly right. So when we talk about terminals, or it doesn't have to be electrical, there could be other components, but when we talk about normally open or normally closed is in its de-energized state or unactivated state, right? So normally open, if this becomes energized, normally open, the normally open contact becomes closed. There's an illustration of what we might see for like a defrost contactor. So this illustration is meant to sort of look more like these two relays on the left here. So what we have here is we have incoming line voltage. Terminals are most commonly, for your incoming line, most commonly labeled L1, L2, and L3. You may also see H1, H2, H3, one of those two. And then your outgoing load is commonly labeled T1, T2, T3. And we have a set of contacts here that are open. Now, in these types of relays here, these are typically not normally open and normally closed. I think these are called Form A type relays. So they just have one position, open or closed. If it has three positions, normally open and normally closed, those are called Form C relays. So I'm representing a Form A relay here, but this has normally open contacts, right? And so it's de-energized in this illustration. Then we have a control circuit, which in the instance of our S3C controllers would be a 24-volt output. Okay, and so then if we are in defrost, what we would be doing is applying a voltage across this A1 and A2 terminal, which will energize the electromagnetic coil here. And then once that electromagnetic coil is energized, these contacts will close and current will flow for defrost, or it could be also fans, it could be whatever, but that's pretty much, that's how that works. So I think I covered that. I think I already said something about the total connected load. If it exceeds the rating of the contacts on our SSC or solid state controller, a remote relay must be used. Another benefit of using a relay over making a direct termination to the controller is it isolates the controller from potential issues with the circuit. I think I could make the argument that our line voltage circuits, our lighting circuits are more exposed to manipulation than maybe the control circuits are. Maybe not, but I'm just sort of thinking out loud here that if you have a short circuit on your line voltage, which is carrying a higher current, and you're connected directly to the S3C controller, there's more of a likelihood that you're going to damage this controller. Whereas if it runs through a contact, you're isolating that circuit from the controller itself. And so it kind of protects what I would imagine to be more expensive parts. I don't know what these cost, but certainly more than a relay costs. Okay, so those are relays. Liquid line solenoids. So the liquid line solenoid opens and closes to control the flow of refrigerant, right? So just like contact opens and closes to allow or restrict the flow of current, the LLS will open and close to control the flow of refrigerant. So if we want refrigerant to flow and the valve is a normally closed valve, what do we need to do in order to allow refrigerant to flow?
Energize it.
That's correct. That's correct. So why would a liquid line solenoid be designed as normally closed? And I don't know that they are in all instances, but why might they be designed as normally closed?
Because when you disconnect power, it closes to stop the flow of refrigerant.
Yep. So that would be the control function. There's also a safety function to that. So if you lose power to your controller, you wouldn't, and you have a compressor somewhere else in the store still pushing refrigerant through a system that's not running fans through the evaporator, and thus fully activating the vapor to liquid cycle, right? You'd want to stop flow through that controller, and so if you lose voltage, it will default to close, and so that's a common safety function to circuitry, that you would choose a device that defaults to its safe position.
Yes.
And so these should be closed during the defrost cycle. I think I might have said that backwards. Nope, I said that right. They should be closed during the defrost cycle and open during the cooling cycle.
Correct.
All right, temperature sensors. Temperature sensors, they're used as inputs to control devices. Right, so if we go back to our illustration up here, you can see that we have a terminal block on our S3C controller that takes inputs from various types of resistors, right? We have coil outlet, discharge air, return air, defrost termination. We have inputs to our S3C controller from resistors. The temperature sensors are, I think that sentence is, temperature sensors are resistors. Yeah, they are. Why? How come? How does that work? Why is a temperature sensor a resistor? Or why, maybe a better way to say that is, why is a resistor used as a temperature sensor?
Because it regulates voltage.
That is an interesting perspective. That's true, that resistance can regulate voltage. there may be instances to where you may be controlling, and so when we think about lighting controls, right? Of course, more with solid state controls doesn't quite work this way, but if we look at a type of dimmer switch, let's say for an old incandescent style bulb, those basically use a rheostat, right? So it's a rheostat allows you to manually change the resistance in series with the circuit, right? And by having a higher, by doing that, you control how much current can flow, or actually, because it's in series, you control how much voltage is dropped across that resistor, meaning there is less voltage available at the load, therefore it will dim the light. Right. So that's a way of controls that as electricians we're very used to. What else might be a physical change that happens to a resistor as temperature changes, or I'm not really quite saying this. With different types of materials are affected differently by this. I believe it's called like coefficient of resistance or material coefficient of resistance. I'm not saying that quite right, but it's something like that. And so that as temperature changes, the electrical resistance of the material will also change. So if you're familiar with having to perform a adjustment factor on our wiring based on ambient temperature, I don't know if anybody has learned about that, but there's sections in the code that require us, if we are running conductors through an area that is of an elevated temperature, then we have to apply an adjustment factor to the conductors, because as temperature increases, the resistance of that conductor also increases. And so that the fact that the change in temperature directly affects the resistance of the wire means that a solid state controller can measure the resistance of the wire and then make a correlation between the resistance of the wire and the actual temperature. I don't know if I explained that well. Does that make sense, or does?
I'll just add this, Phil, real quick.
Yep. Mm-hmm.
The sensors that we used are based on a set ohm rating. And
Okay.
as you said, with the temperature change, obviously that ohm rating or that resistance will change. And these computers are set up, whether it's an S3C or KE2 or whatever the case may be, they're set up to read the change in ohms linearly, if you will, and it can adjust and measure temperature based on that ohm rating. So every little bit of temperature change on that sensor changes the ohms on that sensor, and that's how they read that, if that makes any sense.
Oh, that's perfect. Yeah. So like you could say, if of course this math is not right, but like if 1,000 ohms equates to, let's just say 50 degrees, then 2,000 ohms, if it could even scale in that to that degree, then 2,000 ohms would mean 100 degrees.
And that's correct. And most of these sensors are, in fact, 2K or 10K. And they're set, whatever the computer designates that 10K to be a max temperature, then it reads on a scale from there.
Excellent. Okay. And so this was something I couldn't locate, and I sort of landed in my mind that it's a set point that we determine when the system is programmed. But do various inputs need to be of a specific type? Let's like discharge air versus return air versus other types of inputs.
Typically, they'll set them all the same.
Okay.
They do have, in some instances, they have different temp rating sensors, but in most cases there, you're looking at a milliamp reading and not a ohms or a resistance reading.
Yeah. So very good. I think that we covered that fairly well. We have, so, depending on what your temperature sensor is meant to read, you just pay attention to where it terminates on the S3C controllers. I have some examples here of discharge air, where that would terminate versus your defrost termination. versus your return air terminations. Of course, this can always change. These form factors are taken from a PDF document that who knows when it was printed. So, and this isn't like only with S3C controllers. Like I said at the beginning, it could be a Novar system, could be any different type of system, but these components are all going to be part of the system, so that even though the controls change, the components and their interrelationships with each other don't change so much. And so you could carry some of this knowledge from a spoiling system to a Novar to whatever other systems are out there. So the illustrations I have here are color coded. Now I don't know what resistance values each of these color codes are, but these sensors have a wire that's of a different color. And I totally made an assumption when I was putting this together. Am I right, Jason, in that these colors would indicate the resistance of the sensor?
The resistance is pretty much going to be the same.
Okay.
It's just strictly a color code as to where you're going to locate the sensor in the case, in this instance with the S3Cs.
Okay, so I'm wrong on that that respect. So this is more done just for identifying what sensor is what.
Yeah, it's for ease of install more than anything. Now, that's just this S3C controller. Obviously, on some other controllers, you can have different resistance sensors. It's just typically they try to keep them all the same.
Gotcha.
So that you don't have to have a specific sensor for a specific situation.
Makes
Now, in
sense.
this example, it shows that defrost sensor with the brass bulb. It does look a little different, but that's just for the mounting location. The ohm reading is the same, if I remember correctly. So it's just that's for the mounting location on the coil versus just somewhere in the case on a sticky back zip tie half the time.
Yeah, and I can see it has like a little indent to where zip tie might go so it doesn't move, and a little circular cutout so it sits more naturally on a pipe, maybe gets more surface area against the pipes to get a better reading.
Exactly.
So they may be color coded, which or there'll be some indication somewhere on the device as to its rating. And so here's an example of one that actually is a 3K resistor. So you just need to use the right resistor for the system and the inputs that the controller is going to require. Okay, so we also have in our systems EEPR valves, also which is an electronic expansion pressure regulator. And the electronic expansion pressure regulator maintains pressure in the evaporator coil at predetermined set points. So what will opening versus closing do to pressure?
Hey, Phil, this is Matthew.
Yeah.
That's an electronic evaporator pressure regulator.
Oh, what did I say?
You got expansion in there, which we use on a different valve.
I'm
this
sorry.
one is evaporator.
Electronic evaporator. So electronic evaporator pressure regulator. So this maintains the pressure inside the evaporator. Not necessarily just anywhere on the system is specific to the evaporator then. So what will opening versus closing do to the coil pressure? If it's open, your pressure should be lower, right? And as it closes, coil pressure should increase.
That's right.
Correct.
Okay. So via the controller, inputs from the discharge air temperature sensor or the pressure transducer sensors, which we haven't talked about the pressure transducer yet, but those inputs are used to determine the coil pressure. So why would temperature be a useful input to control pressure or to control pressure or something? Why would temperature be a useful input for controlling pressure? Pressure is directly relational to pressure. So as temperature increases, pressure should also increase. And so we have our discharge air temp sensor feeding the controller an input of what the temperature is. And then that temperature then can be used, or that resistance value can be used to correlate to the temperature, or to the pressure, and then the EEPR will be controlled to open and close. So I'm explaining this from the perspective of an electrician, and so that we can sort of understand, well, what is this device? What is its purpose? And by controlling pressure, we can regulate the specific temperature within the evaporator. And then, of course, I think we need to because you want to maintain a certain level of condensate versus versus vapor inside your condenser. Am I understanding that correctly? So you don't want it to flood, right? You don't want it to be full liquid. You want it to be at least what, a percentage vapor?
Well, in this
Yeah.
instance, oh, go ahead, Matthew. You're probably better
Yeah.
versed at it than I am.
I got a little bit on the refrigeration side. So you're kind of crossing up a couple ideas there, Phil. They're
Mhm.
not wrong. But let's separate how much liquid is in that evaporator. That's a function of your expansion valve, not the EEPR. So
Okay.
the EEPR is going to set our pressure in that evaporator, and we have a boiling temperature of that refrigerant that is equal to that pressure. So pressure equals temperature as far as the temperature that the refrigerant will boil. So that's going to set the evaporator's temperature. That's what the EEPR is. The amount of refrigerant that we're using to do that is a function of the electronic expansion valve,
Okay.
which you haven't covered just yet, but I'm guessing that's coming up.
Yeah. Yep. Okay. Great. Awesome. Yep. So these components are used in conjunction with each other to keep the system in check, right? So EEVs, we have. So this would also be. Now, would this also be electronic evaporator, or would this be expansion? I don't know where I got expansion from.
That's an expansion valve.
Okay, that's where I got expansion from. Okay, so electronic expansion valve. We have two different styles. I don't know that we see these as commonly with case lineups. I'm not sure that we see these that are electrically controlled.
We do see quite a few, and they have a couple different versions. One, like you show a picture of, that's a stepper valve, and then another one that's a pulse valve, which is essentially a solenoid valve, like a liquid line solenoid valve, or it works the same way, but it's
Right.
controlled differently.
Right. Okay. Yeah. So the steppers, from what I've studied, is that they have predetermined positions that they open. So I don't know what they might be, but just for the sake of coming up with something, let's just say 25, 50, 75, there may be predetermined set points on them. I don't know I don't know if I'm getting that quite right, but. And then where the pulse EEVs, like Jason said, they're a solenoid, so it'll pulse. It'll get an electrical pulse to open, and then it'll close, open, close, open, close, and so it pulses to control the flow of refrigerant. And I think they have different terminals that they land on the controller, whether they are pulse or stepper style.
Correct.
Yeah, so there's a terminal here that says for stepper valve. I mean, this is really blurry, but there's different, they terminate in different locations. There will also be pressure transducers. Again, this may not be present on every system that we see, but they're used in conjunction with an EEV or when controlling an EEPR off of the pressure. From the S3C documentation that I've read, and from what I can tell from our drawings, it looks like we are typically controlling the EEPR off of discharged air temperature and not off of a pressure transducer. You guys want to speak to that a little bit?
That is correct. They use the pressure transducer for the superheat calculations for the EEVs, or just to monitor superheat in a lot of cases where we only use a mechanical expansion valve.
Okay. Yep. So this would just be another input. Oh, somebody else has something?
Yeah. So the other thing I'd add to this is this is programmable in the, with your app on your phone, or however the customer wants to set it up. It can be controlled using pressure. It can be controlled using temperature, or it can be controlled using all three. And it really depends on the customer. We just set up one that uses a different strategy. So, just be aware that the customer may dictate which of those three modes, and it's just a selection that you can make in the app.
Very good. Okay. And then I think this is the last sensor that I cover, is the RH ambient temperature sensor. This would be one type of sensor that would be used to control anti-sweat on a case that has anti-sweat and a need to control it. Since y'all are here, I'm going to defer to you guys if you want to say anything about anti-sweat controls.
So a couple points on this. The S3C obviously has the capability of doing this. For some reason, I haven't seen anyone actually use it yet. So there are several systems that pulse the anti-sweats. They're usually, today anyway, used independent of the S3C. I'm talking about like a sweat miser or the manufacturer building in its own humidity sensor to measure that dew point and calculate how much heat to pulse. But the S3C absolutely has the capability to do it. I fully expect in the future we'll see that actually being used. But today it's pretty rare if you do find one.
So do they just, so these pulse the anti-sweat. So it's a pulse signal on, off for the heat versus just a steady on, off, from what I'm understanding. Why might that be the case?
It's just like the pulse valve. We can send a percentage through an on-off closure by using time. It's the exact same thing, pulse wave modulation, if you're familiar with that.
Mm-hmm.
So in other words, if we're going to run something at 50%, we'll have it turn on for 10 seconds and then off for 10 seconds and then back on for 10. So it's on 50% of the time.
Okay.
Right. So that's the concept. What they're going to do is measure that they're actually measuring the dew point in the air. And let's say the dew point is 52 degrees. They're going to try to heat the frame to 53 degrees, 1 degree above that dew point, so it won't condense water. They'll calculate how much heat they have, and they'll figure out what percentage they need of that heat. If it's 70%, they'll use pulse wave modulation and then turn those heaters on for 70% of their time.
Excellent. Excellent. That's a great explanation. Thank you. Yeah. Well, I was thinking pulse. I was thinking rapid pulse. I was like, I don't understand why it'd be a rapid pulse, but 10 seconds on, 10 seconds off. That makes more sense. Because if you're trying to control temperature within 1 degree, you're going to have that on for a very short duration. Interesting.
Right. And for pulse wave modulation, those time variables can be up to like 3 minutes or so. For like if you're light dimming, some of that old stuff was running on 3 minutes, but most of the time we see that around 20 seconds to 30 seconds refrigeration.
Awesome. Cool. Right. And then the last component I make mention of here is the display module, which so on the right, we have the display module that we see, at least if it was at one of our stores, that's what the display module looked like on the right. And then on the left is what's in the S3C documentation for the module. The exact layout, it may change, of course, but the purpose of this component is to provide a user interface to communicate with the S3C controller, set up certain set points, provide certain overrides to force the system into cooling, to force it into defrost, which is something that we need to develop a almost like a pre-closeout procedure, I think, to where when we do a case lineup and we walk away from it and say to our customer, this is ready for you to put product in, that we've gone through a checklist to say, yes, we've tested defrost, we've tested fans, we've made sure that the lighting circuit is not the same, that the lighting circuit is not the circuit that's feeding the equipment. This is something that I wanted to make quick mention of. This is our most common error on the electrical side, is that when we are providing power to these controllers, which I'll make 2 points. One is we don't bring 120 volts to the S3C controller. We bring 120 volts to the power supply that feeds the S3C controller.
Well, that's not necessarily true, Phil.
Is it? There's some variability to that?
It feeds the S3C controller transformer, that power supply, but it does also feed the fans, the liquid line solenoid.
You're right. Yep.
And that's one thing I would add. And they do, when they started this with the S3Cs, they did have a checkout procedure, and I've been trying to locate that. And maybe it's in our specs or something along those lines, but they did have a small checkout procedure where you could go through and verify temp sensors are in the correct place and check functionality, your liquid line solenoid, your EEPR, all that sort of thing. That's more a refrigeration thing because you kind of have to have gauges to see that, or you have to have the app and be able to verify that transducer is reading correctly, all that sort of thing.
Sure.
But what I would say on for the electrical side, as far as just connecting the case, the one thing we need to do more than anything, especially in a store like 4211 where we have multiple circuits feeding the case,
Hmm.
we need to turn those circuits on one at a time and verify that that's what they're running when we turn them on. So if we have a fan circuit, let's turn the fan circuit on, make sure that the fans come on and the S3C is powered up without the lights on. Then let's turn the lights on and see if that works. Now, in a lot of cases, they're doing away with those separate circuits and the 120 feeds everything, and that's
Mhm.
great. But in the stores where we actually have lighting control, if we mess up and hook up the lights and the fans backwards, now we've got a serious problem because every night at midnight, our cases are shutting off.
Right.
So that's the one thing I would say. The most important thing to check would be there.
In this illustration here, what we're seeing is an instance where one circuit feeds everything, right? So you have your line voltage coming in here to feed the power supply, which then in turn provides a 24-volt DC input to actually supply power to the controller. That would be like the computer's onboard voltage that it's going to use to operate. So the line voltage would first hit your power supply, which would step down the voltage and convert it to 24-volt DC and then feed it. And then also, and this was Jason's point, is that also that line voltage does hit these Form C and Form A contacts where we're controlling the liquid line solenoid, fans, lights, and the electric defrost coil. So we would also have, in this instance, the entire circuit feeding this controller would be an unswitched circuit. There would be no controls between the circuit breaker and feed to this circuit. The controls are introduced at the controller, right? So your line voltage comes in. In this instance, it's hitting your defrost terminal. It's coming back on a normally open contact to complete the circuit back to the coil, close the coil, turn on defrost. And then the same thing with lights, fans, liquid line solenoids. That line voltage is controlled through these contacts. Now, there's cases when we're doing case changeouts of existing stores where this would not be connected to the same circuit, right? And so this circuit, in all cases, where it's coming in and feeding this controller, this is really hard to get straight with a mouse. This should be unswitched in all cases. This should never be switched. So what Jason is saying is that when we hook up our power, oftentimes when you have multiple circuits, we have a lighting circuit that's existing, and we have a fan circuit that's existing, and we may have an anti-sweat circuit that's existing. The only circuit of those three that should be controlled in an existing situation, well, this might not be true necessarily because anti-sweat, defrost, those types of things may come from an existing controller, and this gets a little bit more to explain. So I'll just condense this down to say that this circuit that's feeding the power supply has to be unswitched. And so we need to verify that this, when we walk away, that we are not killing power to this through our lighting circuit. And then what makes this a little bit of a challenge, it's not a big challenge, but what causes the confusion in a lot of instances is that during the construction process, our stores are typically, the building automation system will override lighting to on. So our lighting circuits never turn off during construction. And then after our construction period ends, the building automation system returns to normal operations. And then the light circuits start turning off. That means power to this power supply becomes interrupted, which means that the controller doesn't have power and the fans don't have power. Like nothing has power, or at least these contacts are never going to close because the controller is not getting power while the lights are off. And so that's something we really have to make sure if we can get that right and not have that issue, we will have solved probably 90% of our problems with hooking up these cases. But you may have situations whereas this drawing shows one circuit feeding everything. If we have existing circuits, then you would just have, like this light circuit would be its own circuit coming in, and then this is where your lighting circuits should terminate. got this quite a little bit wrong, but your line voltage should terminate across this coil. Your neutral would go directly to the lights, so on.
I'll add one thing to that, Phil. When you were talking about terminal blocks earlier, when we do have stores where they do have multiple circuits feeding a case, typically the case is going to come in wired for one circuit anyway, like this shows.
Mm-hmm.
And there will be a note somewhere on the plans that says that we have to remove jumpers. So that terminal block may have a bunch of jumpers in it that tie that common 120 coming in for fans, lights, and anti-sweats all together. And in that instance, we would have to remove those jumpers to put those dedicated circuits in. And I think it shows it right there.
Yeah. Yeah. Unfortunately, it doesn't let me draw while zoomed in. So we'll just, yeah. So in that instance, like what I don't see on this terminal block is where constant power should land. Like I don't see anything here that says power in on this terminal block. It's
You're
just showing
120 feet at the top.
120, 1 in 20 power
yeah.
supply feed in case you play. Okay, so it's labeling it fans here. And so then you would okay, so then on the load side of this terminal, then we're coming off to fans. We'll go
Correct.
into here. It will also have a wire that goes off to the power supply.
Correct.
Okay. Yep. So yeah, it shows these jumpers. And so if you have fans, lights, and anti-sweats, your fan circuit, which should be unswitched, will come and land on fans. Your lighting circuit, which may or may not still be switched by a remote building automation system, would land on your lighting. And then the same thing with your anti-sweat circuit. So it's very important when we show up on the job, and we really should be trying to get opportunities to get to these jobs a little bit earlier and do some labeling on our conductors before we start disconnecting all of our circuits. It's really important that we do get some labeling on those conductors so that these circuits get put back in the right order. But even if you do that labeling, there's plenty of room still for human error as everything's going back together. So we need to confirm by shutting off that lighting circuit, having your other circuits on. And if your lighting circuit is off and then you go to your you could probably just look at the display module, I would think.
Correct.
If your display module is not lit up, then it's backwards. More than likely that's your issue, is it's backwards. So next week we'll go into some building automation system components, talk about things like the ES1 controller, gateway routers, and things like that, the parts that make the system all communicate.